Okay, let's dive right into this. We are unraveling a fascinating scientific detective story today to uncover the definitive proof behind the true nature of light. Now, I want you to imagine looking at the world through the eyes of a super curious student in a friendly science classroom. Have you ever just stopped and stared at the beautiful, shifting colors in a soap bubble floating by? Or maybe you've wondered why a thin, messy puddle of oil creates those brilliant rainbow colors on a wet driveway. Or perhaps you've just noticed those really specific, fascinating light patterns dancing on your walls on a sunny afternoon. Well, today, we're going to demystify all of that. We're tossing out the complex physics jargon, and we're going to use simple, everyday household analogies to understand how light actually works. Here is the map for today's explainer. We'll start with the great light debate, move on to Huygens' wavefront engine, examine the interference proof, explore squeezing the wave, and finally, bring it all together in the unified map. Section 1. The Great Light Debate. So, our mystery begins way back in the 17th century with a massive disagreement between some early scientists who were desperately trying to figure out the hidden rules of the natural world. And the crucial sticking point was this: Isaac Newton's particle theory and Christian Huygens' wave theory made exact opposite predictions about what happens when light hits something dense, like water or glass. Newton argued that light was made of tiny little particles. He called them corpuscles, shooting in straight lines. For his math to work when light bent into water, he insisted those particles actually had to speed up. But Huygens, he argued light was a wave, sort of like the ripples in a bathtub or a sink. And for waves to bend into water, his math demanded they must slow down. I mean, they couldn't both be right. And this right here brilliantly illustrates the smoking gun. In 1850, Foucault conclusively proved that light slows down in water, meaning the wave model officially wins the debate. It took nearly 2 centuries, but by bouncing light off spinning mirrors into a long tube of water, the data was completely undeniable. Light acts like a wave. But that raises a massive question, right? If it's a wave, how exactly does it travel across an empty room? Let's find out in Section 2, Huygens' wavefront engine. Now that we know for sure light is a wave, let's see how it actually works geometrically and basically build the engine that drives it forward. To understand how waves move, we really have to grasp these 3 fundamental mechanical steps that were first proposed by Huygens. Think about when you drop a sponge into a full sink or a bathtub. You instantly see a circular ripple expand outwards, right? That main ripple is called the wavefront, but Huygens realized something incredibly clever about how that ripple manages to keep moving forward. Notice how every single point on that primary curve is acting as a brand new source, emitting its own spherical wavelets that combine to form the next wave. Just imagine thousands of microscopic pebbles being dropped right on the crest of that bathtub ripple, creating thousands of tiny new ripples. The outer edge, where all those tiny new ripples overlap and connect, that's called the envelope, becomes the new main wave pushing forward. That right there is the literal engine of light. Comparing these side by side is super helpful. You can clearly see how the physical delay of a wave front entering a denser medium causes the bending effect. This is exactly how prisms and lenses manipulate light. If a wave hits a thick glass lens at an angle, the bottom part of the wave entered the glass first and slows down. Think of it like the wheels of a shopping cart suddenly hitting a patch of really thick mud. The top part is still out in the air, moving fast, so the whole wave physically pivots and bends. This exact geometric delay is the secret behind how your eyeglasses or contact lenses use physical shapes to focus light and correct your vision. Moving on to Section 3, the interference proof. Having established exactly how waves move and bend, let's examine the ultimate, undeniable proof of wave behavior: interference. But before we look at the experiment itself, we really must understand coherence. This is the absolute prerequisite for stable wave patterns to form. Basically, if you want to see waves truly interact, they have to be singing the exact same song, perfectly in rhythm. Notice how those chaotic lamps on the left just sort of add their brightness together in a messy blob, while the coherent laser on the right creates stable, beautifully structured fringes. Think about how sound waves behave near kitchen appliances. If you turn on a blender, a microwave, and a dishwasher all at the same time, you definitely don't get a beautiful symphony. You just get loud, incoherent, chaotic noise. Regular light bulbs are exactly like those noisy appliances, but a coherent source, like those common laser pointer experiments you might have seen, is perfectly locked in step, creating beautiful, predictable wave patterns. Now this is where the magic happens. When crest perfectly overlaps crest, we get maximum brightness. But when crest overlaps trough, the waves actually destroy each other to create complete darkness. Notice how the bright red and blue peaks on the chart overlap to build a massive constructive wave. It's like 2 friends pushing a swing at the exact same time. You go higher. But look at that bottom graphic. Have you ever wondered how noise-canceling headphones manage to block out loud background sounds? Well, they use this exact principle of destructive interference. The headphones literally listen to the noisy environment and instantly play a sound wave that is the exact opposite, a trough to perfectly match the noise's crest. They cancel each other out to zero. And guess what? Light does the exact same thing. Look closely at point P on the right. The tiny extra distance one wave travels compared to the other, we call that the path difference, entirely dictates if we see a bright band of light or a dark shadow. Imagine Thomas Young, an early scientist, standing in a dark room, poking two tiny pinholes in a piece of cardboard. The light from those two holes overlaps on the wall. Where the light waves travel the exact same distance, crest meets crest, and you get a bright light pattern. But if you step just a fraction of a millimeter over on that wall, one wave has traveled half a step further. Now crest meets trough, and they physically cancel each other out, leaving a dark stripe right in the middle of the light beam. The crucial takeaway here is that energy isn't actually being destroyed in those dark zones. It is merely being redistributed across the screen into the bright zones. This completely blew the minds of those early scientists. Adding light to light can actually create darkness. Crazy, right? And this exact wave interference is why we see those beautiful shifting colors in soap bubbles and oil puddles on driveways. The light bouncing off the top of the oil film interferes with the light bouncing off the bottom. Some colors constructively interfere and pop out super bright, while other colors destructively cancel out entirely. In fact, modern thin film coatings on your glasses use this exact math intentionally to cause destructive interference and block annoying glares. Section 4. Squeezing the wave. Okay, let's dive into a bit of an edge case that totally breaks our everyday understanding of shadows. It's called diffraction. What actually happens when we squeeze these waves into tight spaces? Well, when light is forced through a tiny opening, it goes through a 3-step process that literally prevents it from traveling in perfectly straight rays. Think about being in a theater. Theater acoustics rely heavily on wave patterns. If an actor speaks on stage, the sound waves squeeze through the proscenium arch and bend outwards, which is exactly why people sitting way off to the extreme sides can still hear them perfectly. Light acts in a very similar way. Look closely at the open slit in this diagram. Every microscopic point inside that opening is acting as a secondary source, interfering with itself to bend the light around the corners. Even if you only have one single opening, like an open doorway, the wavelets on the left side of the doorway interfere with the wavelets on the right side. The wave essentially fights with itself, causing the energy to fan out and bleed into areas that should, geometrically speaking, be in total shadow. And this brilliantly illustrates why a shadow is never perfectly sharp. The finite resolution of literally all optical instruments, even massive space telescopes, is fundamentally limited by this blurring effect. Because light bends when it's squeezed through the tiny pupil of your eye, or the aperture of a camera lens, a single sharp point of light will always spread out into this blurry, rippling peak. It's not a flaw in the lens, it's a hard, physical limit set by the universe itself. And finally, Section 5, the unified map. Now that we've decoded refraction, interference, and diffraction, let's bring all these clues together to answer our fundamental question. While sound waves push and pull back and forth like a slinky, polarization proves that light is actually a transverse wave. That means it vibrates perpendicularly to its direction of travel, which brilliantly allows us to filter out specific angles. Imagine you're shaking a jump rope up and down to send a wave to a friend. If you put a vertical picket fence in the middle, the up and down wave passes right through the slats. But if you shake the rope side to side, the fence blocks it entirely. That's exactly how polarized sunglasses work. They act like that fence, blocking the horizontal light waves bouncing off the road to cut the glare. This magnificent map connects our entire journey, acting as a grand recap for our key findings. From Maxwell's transverse nature to Huygens propagation, Young's interactions, and those inherent limits of diffraction, we've clearly seen how light isn't just a simple straight beam of particles. It's a dynamic, spreading, interacting phenomenon. By treating light as a wave, we can perfectly explain the bending of lenses, the rainbow colors of oil slicks, the dark gaps in laser beams, and the fuzzy, blurred edges of shadows. So, as we wrap up today's explainer, I want to leave you with a bit of a provocative thought. If something as simple as a beam of light is actually this complex, what other everyday illusions are hiding incredible microscopic realities just waiting to be uncovered? The next time you look into a mirror, or put on a pair of glasses, or just watch a delicate soap bubble drift by, I want you to remember the invisible, microscopic dance of waves that is secretly making all of that everyday magic happen.